I think we can start now. Ibrahim. Ibrahim, we cannot hear you.
Yeah, it's my mistake, Alok. I'm so sorry.
Okay.
So should I go back?
Yes, sure.
Yeah, I was talking about learning mode, for example. There are three approaches. We can use batch gradient descent, or stochastic gradient descent, or mini batch gradient descent. In a stochastic gradient descent, we try to update the weights one time for each data point, for each example from the data set. So for example, I have a learning data set which is 100 points, for example, and I decided to train my model for 20 iterations. So in this case, I need to update my weights 100 times 20, in fact, 100 times 20. So it will be like 2,000 times. If you will go for batch gradient, what will happen for batch gradient? In batch gradient, I will not use the gradient itself, but I will calculate the gradient, mean gradient for the entire data set, and I will perform my one update each iteration. So if I will train my model for 20 iterations, I will update the weights only 20 times during those 20 iterations. So compared to stochastic gradient descent, in a stochastic gradient descent, I will update my weights for 2,000 times. But in batch gradient, it will be only 20 times. So in this case, I will get a learning curve which is less noisy, in fact. So it will be more robust. In fact, I will train my model, and hopefully we will be able to converge within those 20, but the learning curve will be more robust, not noisy. So the idea here from batch gradient and the stochastic batch gradient is the hardware which is available for us. So if you try to implement your model on a low power computer, small computer, for example, Arduino, for example, you have very small memory. So in this case, maybe you will go for stochastic gradient because you need to get one example, you need to do your calculations, update your weights, and go to the next example. Delete this example, remove it, and get new example and do another update and so on. So in this case, I don't need too much big memory. In fact, I don't need big memory because I can just use a stochastic gradient descent, which is called also online learning. But in case of batch gradient, you need to be sure that you have a memory which can handle your entire training data set. Because I need to keep my training data set in my memory, calculate the gradient for each example, and after that, calculate the average gradient, and update the weights one time, and go to the second iteration and repeat this process. So in this case, I need to have a big memory where I can store all my data points in that memory. So the trade-off between the two approaches, it's something called the mini batch gradient. And in the mini batch gradient, we can divide the training data sets into number of batches. And the number of data points inside each batch, it will be based also in your memory. So for example, if you are working with video images, for example, or videos or images, for example, so you will see what is the size of each video or each image, and you will decide how much my memory can handle. For example, it may be 10, 20 videos, for example. So in this case, you will reduce the batch size into 20. So if you have 200 data points, and if the mini batch size will be 20, in this case, we will divide the data into 10 batches. So in this case, you will update your weights one time each batch. So in this case, it will be 10 times time 20 iterations, so it will be 200. So it's a trade-off between batch gradient and stochastic gradient descent. And it's based on the hardware which is available to us. So gradient descent is a very nice approach, but now we need to discuss what are the problems with gradient descent, in fact. So if this one is your error function, which we need to minimize. This is my loss function, which we try to minimize, and I can make it like this one. So, and this is omega, for example, right? And we need to reach, in fact, this one is omega star. This is the optimum value, which will minimize the error function. So error here is minimum, and I need to reach this point, in fact. So imagine if you are starting from the left side here with some initial values, maybe it will end up here in that local minima. But this is not where we need to stay. We need to reach that point, not that point. But the problem here, if you are using a gradient descent, using this equation, so theta equals theta or omega equal omega minus eta multiplied by the gradient, at that point, we call it the saddle point. This gradient, it will be 0, in fact, right? Because the slope here will be 0. So this value here will be 0. So you can stuck in that place, in fact. So using a gradient descent, it's easily to stuck in any local minima. And in this case, you will not be able to reach the global minima, which is where we have omega star. So this is the only problem with gradient descent, in fact. And to fix this problem, we need to use something called momentum term. And this momentum term, in fact, it will allow the optimization algorithm to keep moving, to accelerate the optimization. How can we do this? We need to define a variable, we call it the speed, for example. So it will be beta multiplied by all the value plus 1 minus beta multiplied by the gradient. So if the gradient is 0 at some point, you will have this value which will help you to push you forward. Because at some point here, if we here at the saddle point, this gradient, it will be 0 anyway. So in this case, instead of having delta omega equals 0, so in this case, you will stay here, you will stuck here, you will have this last speed, its coefficient multiplied by the last speed, and this value, in fact, it will help you to push you out from this trap. So you can just go to this point and continue your movement until you can reach this omega star, where the error is minimum. So the momentum term accelerates convergence, smoothing out oscillations, and escape local minimum, which is very important. So this is an example. Do you see this example? So this is the learning rate, in fact. So if you can see the curve. So I'm starting from some place here, correct? And using this learning rate equal 0.8. So yeah, I mean, you stuck at some point here. So this is local, right? Which is a problem, because we cannot reach this, because this is the optimum point. In fact, we need to reach that place. So in this case, we will not be able to reach this point. I mean, the second example here, I guess this is the momentum term. In fact, this is with the momentum term. Okay. So when you increase this value to 0.9, you will be able to reach that place using this momentum term. So without momentum term, you will stuck here. Without momentum term, you will stuck here. But when you have a momentum term, it will push you out from that place. But it was not, but the speed decreases here, in fact. So we are not able to escape from that second local minima to reach this global minimum. But if you increase this momentum term from 0.8 to 0.9, we will be able to reach this global minimum here. So this is a momentum term. So even if we are starting from the other side here, and this is the global minimum, it pushed you out, in fact, but you went back again to that location. So so it will help you to, as much as possible, to achieve global minima. So also this learning rate, so the learning rate we call eta, because delta omega equal minus eta multiplied by the gradient. So this eta value also, some people can say that, I mean, we can start with a fixed value, for example. When you are starting with when you are moving with a fixed step size, you can see here, you have some oscillation. Do you see here some oscillations? So we are oscillating around the gradient. So can you see? So we are moving, and we have some oscillation here, which is dangerous also, because if this one is too high, in fact, if this eta is too high, you will keep oscillating across this optimum value, and you will not be able to converge. So we can use adaptive learning rate, and this adaptive learning rate, we need to start with a large value, and after that decrease it with iteration. So I can lower my speed. So I can use this formula, for example, I can multiply eta by I divided by I plus 1, where I is the iteration number. So you can see here, I mean, the speed is much less, but it's still also not very well. But if we can look into the third graph here at the bottom, I divided eta by I plus 1, which means if we are starting by 0.5, if I put eta equal 0.5, the second eta, in fact, when I equal 1, what will be the value? So it will be 0.5 divided by 2, so it will be 0.25. And each time, next time, it will be 0.5 divided by 3, 0.5 divided by 4. So in fact, we are starting with a large eta, large learning rate, and after that, we will decrease it until we converge. And as you can see in this graph, the speed here is very low. It takes too much, it takes longer, in fact, to converge. but we will avoid any potential oscillation around the optimum value, as you can see it here. So if we can look into it one more time, so this one has we have some oscillation around the optimum point. In this example, do you see? We started with high speed, and after that we reduced our speed because we are preparing to land at the optimum point using this adaptive learning rate. So selecting adaptive learning rate approach, it's a very smart to avoid any oscillations around the optimum point. Okay, so now we need to talk about, now we finished this perceptron and the different variations. We talk about this gradient descent, the mode also, batch gradient or stochastic batch gradient and the mini batch gradient. So now we need to talk about first neural network, first multi-layer perceptron. As you can see here, this multi-layer, we can start with one perceptron. Imagine that we have only one perceptron here in the middle. So this perceptron has number of inputs. It could be x1, x2, and x3, for example. This one is connected to this one with a weight value, omega1, omega2, omega3, and we will get the output here. So how can we get the output here? We will just apply the same equations which we got before. So it will be omega x. We need to, to get the output here, we need to get the weighted sum, and after that apply this one to the activation function. So I need to get omega x plus b. So if the weights here, all the weights here called omega1, and if the weights here called omega2, the bias here, all of it called b1 because it's a vector, b11, b12, something. So omega1 here, it will be like this one. Omega1, it will be omega11, for example, omega12, omega13, omega21, omega22, omega23, omega31, omega32, omega33. And the bias here, b1, it will be like b11, b12, b1, something like this one. So it will be in vector notation like this one. So it's exactly the same as a perceptron, but we will just try to expand it. So we have the input layer, and the input layer, it will transfer inputs to the second layer. We have here one hidden layer. We need to calculate the output from this hidden layer, which is called H. So H will be sigma of dot product or omega x plus b. So we need to calculate omega x plus b as we did before. So we will calculate this value, which is the net, if you can remember it. And we will apply this value to our activation function to calculate H. And we will repeat this process for how many hidden layers we have. If we have 2, 3, 4, 5, no problem. We will repeat this process. We can put it in a for loop. And after that, we need to calculate the output layer, the output of the output layer. So the output here, it will be y estimated 1, y estimated 2, for example, or y predicted. So it will be the same. I forgot it, by the way, the activation function. So we have here another activation function. So it will be omega 2h plus p. So it will be omega multiplied by the input, which is the output of the hidden layer, plus bias. And we will apply this one to the activation function to calculate.
So basically what each layer do is to reduce the error? Or...
Yes.
Yes, okay.
Each layer will do the same. We will repeat this process. We will apply the inputs to each layer. To the first layer, hidden layer, we will calculate outputs. We will apply those outputs to the second layer. If you have how many layers, you just need to repeat this process until you calculate the outputs.
And the number of layers depends on what you want, right? It's up to you.
Which one?
The number of layers. How many?
Yeah, yes, it's a hyperparameter. You just need to select it. So it's based on your problem, but we prefer to start. We prefer to start with less number of hidden layers because if the model is too deep, it might overfit my data set. So we prefer to start with a base model, which is a simple model, and after that you can increase complexity step by step. So for example, you can start with one hidden layer, and if you feel that the accuracy is not good enough, maybe it's 85%, maybe you can say, okay, I will try to increase number of units in the first hidden layer. So I selected first 3, and maybe I'll try 5, 6, 7, 8. If you cannot reach the accuracy which you want, maybe you can say, okay, I will add one more hidden layer.
How do you know how many layers are the optimal number?
No, it's a hyperparameter, which means that you need to decide this by trial and error.
Okay.
It's by trial and error, and also there are some optimization algorithms which can, like grid search, for example. So I can use some tool which can do this process to automate this. It will not optimize, in fact, but it will try different combinations. So I can use a grid search approach, and this grid search, it will try to optimize number of hidden layers number of units in each hidden layer. So instead of doing it manually, you can just have an algorithm which will try to do it for you. Here, once you calculated the output, you will calculate, we need to define a loss function. And this loss function, we call it L, for example, it will be this y minus y estimated square. I mean, just we can multiply it by half, multiplied by this, by summation, right? Sorry, it should be half multiplied by summation of y minus y estimated square. So this is my loss function. And now we need to do gradient descent to optimize this one. So for example, I want to adjust this weight value. I will call it omega. This is omega 1, this is omega 2. This is omega 1, this is omega 2, for example. I need to start from the output layer, omega 2. So I need to calculate the gradient first. I need to calculate partial L by partial omega 2. So it will be partial L by partial y estimated multiplied by partial y estimated by partial omega 2. So I need to calculate this value first. Once you calculated this value, you will adjust your weights using this equation, omega 2 equal omega 2 minus alpha or minus eta multiplied by this gradient. You will do this for omega, you will do it also for B. So it will be done using those equations. After adjusting the weights of the output layer, you need to adjust the weights of the hidden layer, those weights, omega 1. To do this, you need to calculate the gradient with respect to omega 1. So it will be partial L by partial omega 1. We need to use the chain rule because the distance is larger now. So partial L by partial omega 1, it will be partial L by partial omega y estimated multiplied by partial y estimated by partial h multiplied by partial h by partial omega 1. So I need to reach omega 1 using the chain rule. Once you calculated this formula, you will use it for adjusting omega 1 and B1. If you have many hidden layers, you need to repeat this process for each hidden layer. So the problem here, in fact, vanishing gradient means this value will get smaller when you are deep. When you go deep, do you see this multiplications? Partial L partial y estimated multiplied by partial this by partial this. So the chain rule will be very long, in fact, when you have many deep, many hidden layers. So at some point, this value will be very, very small. And if this value is very small, close to 0, what will happen? We will not be able to adjust weights because omega will equal loss to omega minus alpha multiplied by 0. So in this case, some layers will not be able, we will not be able to adjust the weights of some layers because the gradient becomes very small. And this is the problem, in fact, when they developed this deep learning stuff, they found this vanishing gradient, so they build the models, but those models they cannot learn because the vanishing gradient problem. So, and when they invented this ReLU, rectified linear unit activation function, which is like this one, this function is very well, it performs very well with this gradient, vanishing gradient problem. So it helped us, in fact, to go deep as much as we want, as we do today, in fact. So without this, activation function, it will be very, very difficult to train the models because this value will be very, very small value, close to 0. And then when it's 0, the model will not be able to train. So it's like someone, he is very tired or sleepy, for example, he just keep reading and studying, but he is not focused. So he will not be able to catch the concept or... if we need to implement this one in Keras, if we need to implement feed-forward neural network or multi-layer perceptron in Keras, it's very, very simple. But I'm sorry, because I was supposed to give you an example from sklearn, because sklearn it's much simpler. Because in sklearn it's ML multi-layer perceptron. It's called ML perceptron, which is much easier, but no problem. But for this example, imagine that we need to build a feed-forward neural network for classifying the iris dataset. The iris dataset, we have 4 inputs, as you can remember: petal length, petal width, sepal length, and sepal width. And we need to build a model which can classify those input species into 3 classes. So now our problem is multi-class classification. So if I can go back, show you the dataset just quickly. So this is iris dataset. Yeah, this one, do you remember it? We have 150 data points, we have 3 classes, and we have 4 input features. The first one, the second, the third, the fourth. The first and the second, it's petal length and petal width. The second, the third, and the fourth, it's sepal length and sepal width. So this problem, we have 4 inputs, and we need to classify those 4 inputs into one of the 3 classes. So we need to build a model which has 3 inputs 4 inputs and 3 outputs. Yes. So this model here, we need to classify this iris data set. So we need to build a model which has 4 inputs. So I will just plot the inputs. So we have 4 inputs: x1, x2, x3, x4. So x1 and x2 those are beta length and width. x3 and x4 those sepal length and width. And we need to have one hidden layer. So I selected here, in fact, a hidden layer with 32 units. Can you see? Very complex. Maybe it's too much. But I just selected a hidden layer here with many units, starting from 1, 2 until 32, which is too much. And I have all those connections, right? And a batch normalization, just forget about this batch normalization. And at the end, I will have, no, there is no batch normalization. And a second hidden layer, which has 16 units, 16 perceptrons or neurons. So 1, 2 until 16, all those connections. So this is the first hidden layer, this is the second hidden layer, and at the end I will have one output layer which has 3 units, neurons or perceptrons. So it's a dense layer which has 3 units. So this one will be class 1, class 2, class 3. This one will be a Setosta, versicolor, virginica. So 1, 2, 3 outputs. So this is my model. So the input to this model will be 4 input features, right? As you can see here in this graph, it's 4 inputs. So this is the first dense layer or the first hidden layer. It has 4 inputs. I mean, it will get 4 inputs and it will produce 32 outputs. We will get 32 outputs. And in the second hidden layer, number of inputs will be 32, and number of outputs will be 16. And for the output layer, number of inputs will be 16, and number of outputs will be 3. So now we classify it. And as you can see here, I selected activation functions. So I selected a rectified linear unit in the first hidden layer, and in the second hidden layer, I selected rectified linear unit, and the output layer, I selected something called softmax layer. So rectified linear unit, I selected rectified linear unit because it performed very well with vanishing gradient. So I will be sure that my model will be able to learn from my data. And I selected softmax because the softmax layer, this one, it calculates the probability that this species belongs to one of the classes, the 3 classes. So the output here, in fact, it will not be 1, 2, 3 or something. It will be the probability. So for example, if I have a species which is Setosta, for example, so maybe in this case, maybe the first output will be 0.9 or 0.85. The second one, maybe it will be 0.05. And the third one will be 0.1. The summation of those should add to 1, which is the maximum value for the probability. So the softmax layer, in fact, it will calculate the probability that this species belongs to that class. As you can see here, this is also more information about the model. So the inputs to this dense layer, it's 32 inputs. The second layer, or the second hidden layer, it has 16 inputs. And the output layer has, 3 outputs. So 32 outputs, 16 outputs, 3 outputs. This is number of parameters. If we need to calculate the number of parameters, it will be similar to the perceptron. If we have a perceptron, we mentioned it before. If you have a perceptron and the perceptron has 2 inputs and 1 bias here, so how many parameters here? It will be 2 times 1 plus 1, right? 2 times 1 plus 1. So it will be 3 parameters. If we need to calculate the parameters for our first hidden layer, how can we calculate it? It will be a number of inputs multiplied by number of units. So it will be 4 multiplied by 32. So this is the number of weights. Are we missing something? Yes, we are missing this bias. Each unit has 1 bias. So we need to add 32. So it will be 4 times 32 plus 32. It will be the total number of parameters of the first hidden layer, which will be 160, if you can calculate it. For the second layer, how many in the second layer? This number, it will be 32 multiplied by 16 plus 16. So this number, in fact, it will be 32 multiplied by 16 plus 16. And for the output layer, it's easy because number of outputs from the first, second hidden layer, it's 16. So it will be 16 multiplied by 3 plus 3. So in this case, we can get total number of parameters. If you can add those numbers together, you will get this total number of parameters, which is 739. We have here something called trainable parameters and non-trainable. Trainable means those parameters must be initialized by 0 value or small random values and should be trained. We need to train those parameters from the data using our optimizer. Non-trainable parameters equal 0 because all parameters here will be trained. This one is very important because sometimes people use something called the transfer learning, and in transfer learning I can transfer a model and you can borrow this model from me for solving another problem. Maybe I have higher computational resources, so you will use my model as it is, or you will make some changes. If you will make some changes, you will get some non-trainable parameters here. You will freeze some parameters and it will be counted here in this non-trainable parameters. If you can look here into those two curves, it's one, I mean, for training my model, I need to divide my data into one part for training and one part for testing. And the part for training will be divided into another two parts, one for training and one for validation. And we need to plot all time the training and validation loss and the training and validation accuracy, because those curves are very important for us. And as you can see here, we are starting from very high loss value, very high error, and with iterations, we trained the model for 200 iterations. We will start going down iteration by iterations until we reach some point where the accuracy will be, or the error will be acceptable. On the other side, we have this accuracy. You are starting from low accuracy, and as you train your model, this accuracy will improve with time. Yes. So this is feed-forward neural network. This one is feed-forward neural network, which is very important. I mean, this is the second step after using the perceptron, which is normal. So now I want to talk about LeNet 5, which is the first CNN model ever. And this one has been developed in 1990 something or 1980 something. This LeNet 5, it consists of 5 layers. So first we have two convolutional neural network. So we have two convolutional neural network convolutional layers. So C1 and the C3. I mean this one and this one. So the C1 and the C3. This is layer number 1. This is layer number 2. And after that, we will have this fully connected layer number 3. This one number 4. And this is the output layer is number 5. They call it LeNet 5 because it consists of 5 layers, 2 convolutional layers and the 3 fully connected layers. Those fully connected layers, it's a feed-forward neural network, like this one. So it's a fully connected layer as the one which we used for classifying iris dataset, exactly the same. The difference here is the first part here. This first part, in fact, it is a convolutional layers. Those convolutional layers, we call it feature extraction. So if you are working with images, for example, you don't need to work with the pixel values. So in this case, you need to use those convolutional layers to extract features from this image. And you will repeat this process several times until you have some high-level features. And after that, you will feed those high-level features to the first connected layer. First connected layer will do some calculation, will send it to the second, and finally to the last one. And the last one here, it will classify, it will do the classification. So classification will be done here. So classification will be done here in that part, and that part will be used for feature extraction. We call it feature extraction. So it will extract features from the image, and it will feed those features to the second phase, which is the classification part. So in fact, this classification part, it is exactly the same as this one. We implemented this one using sequential API, right? So this is exactly the same. They call it dense layer or fully connected layer. So this is the one which we use in classical machine learning or shallow machine learning. We call it shallow machine learning. So in shallow machine learning, we build this feed-forward neural network or multi-layer perceptron for classification. The input here will be features, right? If you want to work here with an image, this number will be very huge. It will be number of pixels in this image. So if I need to use this model with this data set, for example, which is MNIST data set, which is handwritten digits, the image here is 28 times 28 pixels, which is 787, I guess, correct? So if I want to use this model For solving the same problem, I need to increase this number from 4 to 787. And if this one is 787, I cannot use this one 16 or something. I need to increase this number so it looks normal. So at the end, the model parameter here, it will increase a lot. It might be 5,000, 6,000 or maybe 10,000 or something. It will be a very large number. So this number will increase, which means the model capacity will increase. And if you don't have enough data for training such a model, this model will overfit your dataset. To avoid this, we can use those convolutional layers. Those convolutional layers, it will try to extract some features from each image. So we will apply convolutional feature maps, convolutional layer into the input image using some filters, and it will extract some feature maps. We will do some sampling here, average bowling for some subsampling, for example, and we will do another convolution. So at the end, we will get those higher level features. Once we have those higher level features, we will feed those features to the next phase, which is classification part, to classify each image into a digit. So this one, it's a 3. So we should expect that this one 0, 0, 0, 1, 2, and this one 1, and the rest will be zeros. Because at the end here, we will have 10 classes. I mean, the output from this one, it will be 10 classes. So when the input is 0, we should expect a number like this one, 0, 0, 0, 1, 2, 0, 1, and the rest will be zeros. If it is 1, it should be 0, 1, the rest will be zeros. If this number is 0, for example, so it will be 1, and the rest will be zeros. So it should be something like this one. So in this convolutional layers, we use something called the padding equals same to retain the original shape of the input image. I mean, if we didn't use, in the technique here, I will not go into much details, but if you need to keep the same size of the input image, if you need to have a feature map which has the same size as the input, as this one here, in this case, we need to use something called the padding equals same. So in this case, we will keep the same size of the input image. If you don't want, you can just use padding equal valid, and in this case, the feature map will shrink and it will lose some information around the edges. So it's not only keeping the same image size, but also you will lose some information from around the image, which might be important in some applications. We use also something called the stride tool, which is also reduces the size of the image because we move, this is the step size which we use to move our filter. We have also something called the pooling layer, which reduces the feature size and reduces also calculations or number of activations. So this is LeNet, which is the first convolutional neural network. If we need to use this LeNet for training, for classifying MNIST dataset, it's handwritten digits. MNIST dataset, it's handwritten digits. So you have some people who wrote those, numbers from 0 to 10, and you need to build a model to classify those, for example. This model, as we agreed, it's 5 layers. So we need to use sequential API in sklearn, in Keras, in fact, to build our model. So we will have the first convolutional layer. It's called the conv2D. So this is the first layer. The input to this layer, it will be an image, grayscale image of size 28 times 28. We used, as we said, we will use padding equals same. They used a very old activation function here. It's called hyperbolic tangent. We didn't use ReLU because at the time ReLU was not discovered. So they used the hyperbolic tangent. Stride equal 1. The kernel size equal 5, which is 5 times 5. Number of filters equal 6. The second layer, it's average bowling. We will not say it's a layer, but it's average bowling. It do some down sampling, the feature maps. The second convolutional layer, it will be this one. So it's another conv layer, which has 16 filters. So it will generate 16 filter maps from those 6 filters, 6 feature maps, which we got from the first layer. Kernel size equal 5, stride equal 1, activation also equal hyperbolic tangent. Padding equal valid, which means we will allow the feature map size to reduce. In fact, we need to keep it the same only in the first, because in the first, maybe we have very important information across the edges of your image. It will be followed by average bowling again. And after that, we will have a third conv layer. We have a third conv layer here. So we have 3 convolutional layers. The output from this layer will be flattened. So we can feed it to the first fully connected layer. So this one will be number 4, and this one will be softmax layer number 5. We use here softmax again because this one, it will calculate the probability that this image belongs to that class. So the output will be probability, not classes. So if you need to calculate number of parameters, we have this table. If you want to calculate number of parameters here also, it's very easy. So number of parameters here, it will be the kernel size. This one, it's 5 times 5 times 6 plus 5. Because each kernel, in fact, each filter, it's like one perceptron. So it has a bias. And the size of this one is 5 times, so it will be 5 times 5 times 6 plus 6. We should get this number. Average Boolean, it does not have any parameters. This one has this number. This one does not have any parameters. This is the first dense layer, which has this number of weights and bias. If you need to know how can we get this number, so we will see how many units here. It's 84. So it will be in fact this number multiplied by this number plus this number again. Sorry, it will be 120 multiplied by 84 plus 84. We will get this number, and so on. So this is our model, and this is the training and validation loss and the accuracy. So for the loss, we are starting from very high loss value, and it will go down with iterations, with our iterations, until we reach a very low value. When we are satisfied, we can just terminate learning process at that point. For the accuracy, which is the same, we are starting from low accuracy, and this accuracy, it will increase with time. At the end, when we finish training, and we need to test our model. So before training our model, we need to divide our data set into 2 containers. One will be used for training, and one will be used for testing. So this part will be used for training, and after completing the training, we will use that part for testing our model. And we need to plot the confusion matrix, for example. And this confusion matrix, we need to plot the true labels against the predicted labels. So the true labels will be across y-axis, predicted will be across x-axis, and you can see here all correctly classified examples will be listed across this diagonal, this one. So for example, the first one here, it means 972 zeros classified as 0. The second one here, it means 1127 1 classified as 1. This one means 1022 2 classified as 2, and so on. We can see other numbers here, those numbers where the model is confused. So for example, here the model is confused between 0 and 8. So sometimes some 8s are classified as zeros, right? Because sometimes the people write 8 similar to 0. So sometimes also the model will be confused, and it will classify 8 as a 0. And also it can classify also 6 4 times. So 4 cases, we have 4 cases where the model classified 6 as 0, and so on. So CNN, it's very important, and maybe the next step will be a recurrent neural network. And the recurrent neural network, it was first introduced in 1988, but it didn't attract that much attention until, maybe last 10 years, because it requires too much calculations, in fact. So the first RNN was introduced in 1988, and the state can serve, it has a state, and the state can serve as a memory, which allows patterns to be remembered over long-range context. So the idea from RNN, it can work with sequential data, and it has a memory which can memorize, the context along, can memorize the context of the time series. For example, it could be time series, it could be text. So we need to remember the context using this state. There are lots of versions of this RNN. The most simple one, it's called vanilla RNN, which is simple RNN. And the vanilla RNN calculates the output sequence, H1, H2 until Hn, in terms of sequence of inputs, X1, X2, and Xn, and also the initial state, H0. The current state, Ht, also is calculated using the previous states, Ht minus 1. So it can memorize something from the context and the current input, Xt. So this is a very simple equation of it. So Ht, where this is a state at time t, it will be calculated as a function of the current input Xt and the previous state Ht minus 1. And this one also, it can be converted into a decision line, if we can say it's a decision line. So it will be, or net value, for example, so it will be omega h multiplied by ht minus 1 plus omega x multiplied by x plus p. This one, it's a bias. This one, it's weighted sum of inputs, of the inputs, xt. This is weighted sum of the states. And this if it's a nonlinear function, such as hyperbolic tangent, for example, omega h, omega x, and b, this model parameters, which are shared among different time steps. So this is the graph of this vanilla RNN, for example. So this is like a perceptron, and we calculate the output from this perceptron here. The output will be calculated as a function of x and ht minus 1. So here it will be ht minus 1, and this one will be xt, and we will calculate here ht. So ht will be calculated as a function of xt and ht minus 1 using this weighted sum, using those weight values or parameters. So if you want to unfold it, it will look like this one, for example. So this is the RNN, as we said that we calculate ht as a function of xt and the last state, which is ht minus 1, right? Using these equations. And if you want to unfold it, it will look like this one over time steps. So you can say that we send a number of, if it is a time series, for example, so maybe each time I send the 4 values or 5 values, and we'll try to shift 1 step each time, so we can have a sense of the context. This is simple RNN, and this is RNN, in fact. So RNN, it's more complex than simple RNN. In the simple RNN, we use hyperbolic tangent. We use softmax also for calculating probability. So, for example, if you want to train a model to predict the next word, so it will give you the next word with a probability. If you want to implement it in Keras, for example, it's also simple. We can use sequential API for doing this, and it will be 1 layer. And this layer, we call it simple RNN. We just need to write simple RNN. We need to define the number of units, which is the number of states, number of hidden states. This is the shape of the input. So when it's 3 times 3, the first state, it's the number of input words, for example, or characters in the input sequence, or number of time steps. And this one will be number of features, right? Number of features. You can calculate number of parameters of this model. You can build a model where you have 1 layer, which is RNN, for example, because it will consume sequential inputs, and after that you can have a dense layer at the end for calculating some probabilities or whatever. Yes, I guess we are at the end. So thank you very much. I hope that it's useful today. It gave you just an introduction to many different areas of machine learning. We started with a perceptron, multi-layer perceptron, and after that we used the CNN and RNN. And if you need more details, in fact, we can arrange it one another week, for example, and we can go deeply into one of those areas.
Are you recording this class?
Unfortunately, I forgot to record the first part, but I recorded the second part, and I will share it with Alok.
Okay. Also, can you share the presentation?
Link. Yes, I can share, and I can share I recorded it, and I will share the link with Alok after we finish.
Yes. Well, it should be nice to have another class.
Yeah, it will be nice, really. So
Yes.
I'm available. So if Alok would like to have another time, we can just arrange it again.
Okay, thank you so much.
Yes.
Anyway,
so maybe next,
any question, can we email you?
Yes, please. Yes, and if we can, maybe if we can do it another time, we can have examples. So we can work with some examples. So I can prepare some examples from each area.
Yes.
So can you work with data by yourself?
If you can give us examples and
and the code. So
the code, the algorithm. So
yes,
just
it will be very good.
Kind of real cases, or simplify real cases, so we can have like a better idea.
Yes, yes. I have all codes, and I can prepare another time, for example, so we can have one example from each type with a small data set, so we can get hands-on.
Okay, when can we have that class, or we need to talk to Alok first?
Yes, please just talk to Alok, so we can arrange it according to his plan, so we can have it.
Yes, should be awesome. Okay.
Yes, yes. So I'm available. So we just need to arrange, and just let me know when I should do it, and I can just do it immediately.
Okay, Ibrahim, thank you so much. Tusen tak.
Thank you very much. Thank you.
Really good, really good.
Thank you.
I love mathematics.
It's mathematics, but it's basic. It's not very complex.
This is this partial derivatives and this.
Yeah, we can do it one more time. I can share also the link with you, so I can just close. And I can send it to Alok also.
Okay.
So I just need to stop sharing.
Okay. So have a good afternoon.
Yes, thank you very much. Thank you.
Okay.
Yeah,
Bye.
bye. Bye.